Take 137. Good morning. Happy snow day. I wanted to provide you with a couple of videos that go over some of the material that we would have covered today. But you have a homework assignment for these, and you also have a um, quiz on Friday that will cover some of this material. This is the first of two videos I'm going to send out. I'll send this out this morning. I'm going to send the other one out this afternoon. The goal of this first video is just to remind you a little bit about heat and talk about latent heat. We talked about heat and specific heat just before the break. We started talking about that. It's been a little while. You probably need a little bit of a reminder on that. And then want to introduce the idea of latent heat of fusion and latent heat of vaporization. That is the heat needed to first melt ice, for example, and then the heat needed to boil water, turn it into a vapor. All right, so heat and specific heat. So heat is the energy contained in an object because it has a temperature. In particular, if I want to change that temperature, requires a certain amount of heat that depends on the mass, the change in the temperature, and the specific heat of the type of material that we're talking about. So, for example, if I want to increase the temperature of water by 1 degree Celsius, and it's 1 gram of water, then I'll need 4.2 joules or thereabout. So that was something that we went over before class before the break, and different objects are going to have different specific heats. So water, as we already said, has a specific heat of about 4 joules per gram or 4 kilojoules per kilogram per degree Celsius, but it also takes 1 calorie. That's the definition of a calorie, is to heat 1 gram of water by 1 degree Celsius. Bone, blood, the fat will have its own specific heat that I couldn't find any definitive values for. Notice that these are all, bone is the most different, but notice that these are all about the same as water, not much different. Okay, so changing states. Here things get just a little bit different. When you change state, the temperature doesn't change, but you can still add heat. So, for example, in this graph on the right, I have the temperature of, let's say, water and the time versus time. But really, this is what this is on the bottom axis here is heat. So I'm adding heat at over time on a regular rate. And if I start with water as ice, right, it's in a solid crystalline form, so with nice hydrogen bonds, and I heat it up, and its temperature is going to change because it has its own specific heat. So ice is going to have a slightly different specific heat from water. So its temperature increases as we add more heat, but it stays in this crystalline shape. We hit the melting point of water, 0 degrees Celsius, and now we start breaking the bonds between the water molecules. So the hydrogen bonds between the water molecules get broken. The water molecules start to move around independently, but it takes energy to break those bonds. And for 1 gram of ice, it takes 334 joules of energy to break all of the bonds in a gram of ice. So, but while that's happening, the temperature doesn't change. So the ice continues to stay at 0 degrees Celsius, the ice-water mixture, until all the ice is melted into water. And then it becomes water. And the water is still attracted to itself. The molecules are still attracted to itself, but they're able to move around freely. And so now you start to heat it up, going back to our 1 calorie per gram per degree Celsius, so you heat it up by 100 degrees. Whoops. and then starts to boil. And again, we need energy so these water molecules are still attracted to each other. They're still they don't bond in a permanent sense as in ice, but they do form some temporary bonds. They're pulling at each other. To separate them requires more heat. So again, it stays at constant temperature, but now it's over 2,000 joules per gram of water to now turn it into a vapor where all the water molecules are moving freely with each other and really don't interact once they're in a vapor state. Right. A little bit more about latent heat of fusion and latent heat of vaporization. So the latent heat of fusion, so the equation that we typically use is just that the heat needed to melt some mass of ice is that mass times the latent heat of fusion. Again, for water, it's 334 joules per gram. And this is also, by the way, if I want to melt it, I need to put in 334 joules per gram. If I want to freeze a gram of water, I need to take that heat out. So I need to take that energy out somehow and remove that. Notice that once the water is melted, it's still attracted to each other. It can still, the molecules can still form temporary bonds, but they aren't permanent and they can move pretty freely. For vaporization, again, I want to now really move these molecules further apart, get them moving pretty fast. In order to do that, I need to put in over 2,000 joules per gram. Or if I want to condense the water, I need to take out 2,000 joules per gram and get it back into water. So, and now the molecules are zipping around in the air. They're not interacting with each other. And again, the equation that we'll use is that the heat required to vaporize some mass of water is the mass times the latent heat of vaporization. All right. I want to do an example, but I'm gonna have you think about it for a little while and see if you can try this out. The equations are already on this sheet, so on this slide, so you might want to look at it. I want to take 100 grams of ice that's at 0 degrees Celsius, melt it, bring it up to 100 degrees Celsius, and then turn it into steam. So starting at 0 degrees, ice starting at 0 degrees Celsius, how much energy do I need to melt it and then boil it off to at 100 degrees Celsius? So work on that and you'll get the next installment later on this afternoon.